In this part, we're going to study transformation of functions. The word transformation means that we're actually changing functions. And if we understand how a function changes, then a lot of things can be found very easily. We can find any properties of the functions where they have moved. For example, if I know that a function increases in a certain interval and I change it, I know where the interval where it increased changed. If I know that it crosses the x-axis at some points and it moves, then I know where those x-intercepts have changed. So it is always very useful to understand how we're transforming functions. So we're going to talk about different kinds of transformations. What can we do with a function? A function, we can move it vertically, and we're going to refer to it as vertical shifting, which is up and down. We can take a function and move it horizontally. We can take any function and reflect it over an axis. It could be the x-axis or the y-axis. Then we can also stretch a function, which means if it looks like this, if I stretch it horizontally, then it's going to look more like this. Well, that would be horizontal stretching and vertical stretching. So, think of you buying a top that is too short, then you're trying to stretch it vertically. So you're trying to go like to cover every single thing in your body. And then we have even and odd functions, which is something that we have studied before, but now we're going to see it more formally. So now we have vertical shifts. I know that this is not color, so I'm going to highlight the original function. Let's say that my original function looks like this. If I happen to graph a new function, so this is the original, which we're going to refer to as the parent function. If I graph a new function, and this new function looks like the parent plus some number, given that that number is bigger than 0, then I know that this new function would look like the parent one, but shifted upwards. Now, if I have the original function, the same one as I had before, but the new function, so this is the parent, that's the original. If I create a new function that looks like the parent function minus a number, it could be minus 3, minus pi, minus square root of 2, minus 1/2, any number greater than 0. Then what's going to happen is the shape is going to stay the same, but it's going to shift downward by that many units. So the idea behind it is that we are changing every single y value. So let me explain that more thoroughly here. We have to shift these graphs either downward or upward from the original one. So I recognize that the parent function here, or the original function, is the function that I already know how to graph, y equals x squared. And that function looks like this. The vertex is at 0, 0, and then I know that the point 1, 1 belongs there, and then the point 2, 4 belongs there. And I know those things because you get the y by squaring the x. So if your x is 1, 1 squared is 1. If your x is 2, 2 squared is 4, and then for 3 will be 9, and so on. So my parabola would look like this, and I can do the same thing over here. So this is my parent function right here. So if I compare my parent function with this new function that I'm going to call g, there is a plus 3 extra. And if you can see that here, if you compare these two equations, the plus 3 is on the outside of this function. So what happens is, this is the parent function. If I'm adding 3 to it, that means every single y in here, every single y value is being added by 3. That's all it means. But the x's remain the same. This is the point 0, 0, and the y value would also be added by 3. That's exactly what it means. So instead of 0, 0, it's going to be 0, 3. Instead of 2, 4, it's going to be 2, 7. Instead of 1, 1, it's going to be 1, 4. They skip the point. 1, 4. So you can add 3 to every y value, or you can say, well, if it only moved up 3 and it conserves the same shape, I know that the vertex will be here, and I know that I have to go over 1, up 1 here to get the next point. And you know how to get the second point. You went over 2, up 4. So from here I can go over 2, up 4. 1, 2, 3, 4. And get the next point. Or you can add 3 to every single y that you know. That will be fine too. So in here I graphed the point 2, 7. And then the same thing is going to happen on the other side. And then I have sketched my parabola by moving it up 3 units. Now in this example here, what's going to happen to the parabola? This is my parent function, and there is an extra minus 2. So that means every y value in here, rather than adding 3 to it, now I'm going to subtract 2 to every single y. And the x's stay the same. So now instead of the vertex being at 0, 0, now the vertex is going to be at 0, negative 2. So that's where the vertex is. And then I know the points 1 over 1 up, 2 over 1, 2, 3, 4 up, 3 over 1, 2, 3, 4, 5, 6, 7, 8, 9. I can graph all those points because I know what the pattern is for a parabola. And then I can do the same on the other side. 2 away, 2 away, 3 away, 3 away. So I have graphed a parabola with certain points that I know the coordinates of. This is the coordinate 1 or negative 1. This is the coordinates 2, 2. This is the coordinate 3, 7, which actually matches with taking away 2 for every single y coordinate. 9 minus 2 is 7, 4 minus 2 is 2, 1 minus 2, negative 1, and 0 minus 2, negative 2. So that's how I'm going to sketch vertical shifts for this part. For horizontal shifts, the idea is going to be similar. However, the equations are going to look a little bit different. In here, the original equation or the parent function is this one. So that's the parent. And if I have a number that subtracts the x, that means that my graph is going to move to the right that many units. For example, if you see an f of x minus 3, then that means the function moved right 3 units. And then if you see a number adding to the x, then that means that my parent function that was originally here has moved left. Oh, I'm misspelling left. It's kind of embarrassing. Left. That many number of units. Now you can see, compared to the vertical shift, the plus c appear outside the function. In here, the plus c and minus c are inside the function. So how does that look like on the equation? Let's look at example 2. In here you can see the parent function is this one, and in here you can't quite separate that because you don't have an x square. In here, simplify, you have the sum of x plus 4 squared, which you know is x squared plus 8x plus 16. But you don't have an x squared like you did before. Like, I cannot separate that. And that is because the plus 4 is affecting the x-axis directly. So that indicates, because the plus 4 is affecting the x directly, this is a transformation in the horizontal direction rather than vertical. If you had g of x equals x squared plus 4, then this is changing the y values. So that means it's moving vertical, but in here the +4 is changing the input, changing the x values, so therefore the transformation is horizontal. But unlike the other one, this one works kind of backwards, and I'm going to explain why in here. I'm going to show you with my paperclip parabola. So if I have a function like x squared plus 3, that means my parabola moves up 3. Okay, so originally it's here, the parent function is here, so it moves 3 units up. So that's where the graph of x squared plus 3 will end up being from the other slides. If I have another function where it says x squared minus 4, then that means this is the parent function, and I'm gonna go down 4 units, 1, 2, 3, 4, and that's where the parabola x squared minus 4 will be. But what happens when I have a function that is affecting, rather than x squared, to the x before it's been squared? So now my parabola is not the one that moves. In this case, it's the paper that moves. Okay, so this is how it's gonna work out. I have my paper clip on the original position, that's my parent function, but now my paper is gonna move 3 units to the right. So check this out. I'm keeping my paper clip parabola where it is. Well, trying to. Okay, I'm ready. And I'm gonna move my paper 3 units to the right, as I said. So 1, 2, 3. Okay, so what did we notice? As a result that the paper is the one that moved, it appears as that the parabola moved left, and that's exactly what it means. This transformation means the original function moves left 3 units. Although your common sense says +3, oh, that means right, but that's not the case when we have horizontal transformations. When we are affecting the input directly, then it's not the graph that moves, it's the paper that moves. So since the paper moves, it looks like the graph is moving backwards, but it's not, it's the paper that is moving forward. So what happens when I have a function that looks like x minus 4 squared? Well, again, I return to my original position, and now my paper is the one that moves left 4. So in my paper, I'm gonna leave my paper clip steady where it is, and now my paper is gonna move left. 1, 2, 3, 4. Visually, it looks like my graph moved right, but it's my paper that moved left. So as a result, this graph makes the original parent function move right 4 units. Nobody cares about the paper moving. You want to appreciate what's the end result. So the end result is the graph went from here to here. So you say, oh, okay, the graph moved right. But you know with your precalculus brain that actually is the paper that moved, so it appeared like the graph moved backwards in the opposite direction from the paper. So summarizing here, I have my parent function again, and I know where the important points of this is. So now I'm gonna graph them in here. +4 to the x, I'm changing the x value. Remember, is the paper that moves 4 to the right, so actually my graph is gonna move 4 to the left. So I know the vertex is at 0, 0. Now the vertex is gonna be at 0, -4. But then the rest of the points are gonna also move the same quantity, so everything else stays the same. 1 over 1 up, 2 over 4 up. If I have to go 3 over up 9, that will be fine too, if I had the space, but I don't, and I don't have the time either. So I have these other 2 points, and that's the end of the graph of my parabola. Now, This is very easy to do, and I also know some points on this new parabola. So for sketching, and if you're going to take calculus in college, this is very useful information, that you can graph this transformation so precisely without having to think or to have a graphing calculator with you. Now the -2 again is my paper that is going to move left, so it's going to appear that the graph moves right 2 units. So 1, 2 units. Now the new vertex is going to be at 2, 0, but then all the other points stay relatively in the same position as the vertex. So I can graph other points in here. I know that for this equation the point 3, 1 is there. I know the point 4, 4 is there, and some other known points that I have highlighted here. So definitely very useful. So now I have here combining horizontal and vertical shifts, and it says sketch the graph of this function. Now the parent function has changed. We won't always graph x squared, but we're gonna study several functions over the rest of the year. So now the parent function, this is something that we have studied before. The parent function is square root of x, but now 2 different things have happened to it. I see a +4 that is outside the root, so that implies that this +4 is changing the y values, and because it's changing the y values, that means vertical shift. And I see a 3 affecting the input or affecting the x values. So this means if I'm changing the input or the x values, that's the same, I'm changing the input. So that means horizontal shift. I haven't specified yet where, but I know it's going to shift horizontally. Since it's +4, I know that I'm going to move up 4 units. And since it's -3, remember that when I'm changing the input, it works backwards. The paper is the one moving left, so my graph will move right 3 units. Now for square root of x, you must remember what the important points are for that. And this is something that you have to have in your mental library. So square root of x looks like a parabola, but laying down in half of it only. So it starts at 0, 0, then square root of 1 is 1, then square root of 4 is 2. I wouldn't graph the 2 because I don't have a number here that it's an integer. I'm only going to graph the points that I know, the coordinates of 0, 0, 1, 1, and the 4, 2. I can graph the 9, 3 if space allows to do that. So that's the parent function. So now I'm going to do what I said I would do. I'm going to move up 4 and I'm going to move right 3 at the same time. Now which one is done first, it really doesn't matter. So I'm going to graph my xy coordinates, and then since I'm going to move this point right 3 and up 4, 1, 2, 3, 4, now the graph is going to begin there, but it still is going to keep the same shape and the same distance relative to the other points. So I know I'm going to have another point across from it right here, and then from this point I'm going to go over 4 up 2. So from this point 1, 2, 3, 4 and up 2. So now I have graphed my square root function, and it has shifted 3 units to the right and 4 up. And then I'm done for this part.